Good day, everyone, and welcome to another episode of MedTalk, where we talk about all things medical and tech. Today, we have a very exciting lineup of panelists to talk about the revolutionary product which has just entered the healthcare industry. It is called CT-CAD, or CT scan computer-aided diagnosis. But first, let me introduce our panelists. Today, we have Yuan Kai and Justinian, who are product owners and lead developers of CT-CAD.
Hi everyone.
Hello.
Not just them, we also have Dr. Benjamin, consultant from SGH, and Lee Kin Hong, who is a director at MOH.
Hi everyone.
Hi everyone. Really excited to talk about this project.
And of course, I'm your host, Akhilesh. Now, before we go to talking about what CT-CAD is and all this, we have to understand what the problem is all about. So, Dr. Ben, is it really that difficult to do image studies, and is there really so much errors in it?
Yes, Achilles. As a radiologist, I get over 1.3 imaging studies annually, and it is part of our training to come up with diagnosis quickly. CT scans are the best way and the gold standard to actually identify brain bleeding. We actually have a very short time to diagnose issues based on CT scans when we are looking at brain bleeds due to the sheer number of them.
Wow, it must really be stressful to ensure you make the right call on a diagnosis, because this is going to affect a patient's life.
That is very true, Achilles. But when MOH did our study, we do foresee there is a growing to be an increasing in demand for CT scan. This is because of aging population, and there's a potential increase in the risk of diagnosis error due to the limited time radiologists have plus other constraints.
As what both King Hong and Dr. Ben said, we spent a lot of time defining our problem statements in order to try and use computer-aided diagnosis for CT scans.
Yep. We really wanted to bridge technology with pathology by using neural networks to try and classify different types of CT scans.
This is definitely a great way to understand how CT scan can actually help in healthcare. But let's try to understand this first. What exactly does this product do?
Well, our product is a classifier, and this classifier focuses on detecting intracranial hemorrhages or brain bleeds, and along with its broad types like IPH, SDH, and all the other associated diagnoses within the healthcare industry.
In hospitals, these are some of the key scans we use to identify brain bleeds.
CT-CAD classifier really aims to identify ICH and other subsets of the dataset, which really provides a quick computer-aided diagnosis for radiologists to verify these CT scans.
This really sounds good. How exactly did your team produce this model?
That's a great question, Kin Hong. So we begin with a brain CT scan dataset compiled by the Center of Advanced Research in Imaging, Neurosciences, and Genomics, HERING, also located in New Delhi, India.
This dataset had almost 489 hit CT scans, which could be transformed into over 24,000 axial slices in the medical DICOM format. And this is the standard format that is used in healthcare.
Yeah. DICOM and Nifty file format is generally used in healthcare industry as an industry norm today.
In healthcare, we do need to split CT scans into axial slices to get a good sensing of the entire brain in terms of the layers.
This is actually really interesting. In any machine learning models, you always need to do some form of data cleaning or transformation in terms of pre-processing before beginning the training of the model. How did your team go about doing this?
Well, in the medical field, we generally use Hounsfield units, or HU, to determine the radial density in medical imaging. So HU is a scale that quantifies radial density, which is crucial for identifying different tissues in medical diagnosis. So one of the first things we had to do was to convert raw pixel values to HU using the rescale intercept and rescale slope provided in the input metadata.
Next, we further perform windowing on these images to ensure the visibility of sensitive tissues by limiting the range of HU before we start to train our model. So in our case for brain CT scans, the unit ranges from 40 to 80.
On top of that, we also had to perform windowing on the images to ensure the visibility for display purposes and to aid the medical professionals in viewing these CT scans, and also to process the images for feeding into our neural network.
Wow, that's fascinating. But how do you guys go about exploring the whole data set after doing this pre-processing step?
Well, the exploration phase was pretty interesting because we learned a lot of new information about our dataset.
One of the first things that we did was to check the number of slices that is presented in each of the data set.
As you can see, in our entire dataset, each CT scan had an average of 32 axial slices. So we had some CT scans which actually had 450 slices, while others had as low as 4.
Wow. But within the data set itself, how many positive and negative cases were there for the various diagnoses?
So within the dataset, only ICH had a good balance of positive and negative data. All the other diagnoses had quite an imbalance too.
Does this help the team to have a model that focuses learning a particular diagnosis?
Well, you're absolutely right, King Hong. So we wanted to ensure our model was trained on both positive and negative classes sufficiently to ensure a robust model once we deployed it.
Besides the high number of positive and negative cases, we also observed that there is a good correlation between ICH and IPH cases, which encourages us to focus the training to identify specific groups of diagnoses to ensure that our proof of concept that we developed in our model is successful.
But from a medical perspective, are these correlations logical?
Well, definitely. It is common for ICH patients to also have IPH, or as the rest of the data shows, a high correlation between a left and right bleed location whenever there is an ICH in the dataset.
For a POC model, it is definitely a great idea to focus your model on the specific diagnosis to ensure the robustness of the model and to have a good result before scaling it bigger.
That's correct, King Hong. Another reason for us to focus on the ICH diagnosis was the spread of the classes. As you can see, the bulk of the diagnosis besides the bleed left and right class has a significantly higher proportion of data compared to the rest of the classes.
Wow. Thank you so much for explaining the data set, the data exploration phase, and the pre-processing steps you guys went. But now let's go to the more interesting part, which our audience are very interested in, the model itself. How did you guys manage to identify the correct type of model to use?
Right at the beginning, when we were deciding what model to use, the first problem we had to work on is to decide whether we wanted to use a 2D model or a 3D model.
Wow. What is the difference between this?
Yeah. So a 2D convolutional neural network, or a CNN, treats CT scans as individual slices, while a 3D CNN can exploit spatial relationships between the slices themselves.
So in our product, we attempted to use the 3D model first and hope to leverage on the pre-trained network called MedTalk, which is based on the ResNet 18 3D model initially built for video images.
This Med3D team has actually trained their model on a large medical imaging dataset, and the model was specifically designed to be used for segmentation purposes.
The authors of the Med3D paper also showed that it was possible to do classification by transferring the weights from the Med3D model into a ResNet 2D, into a different ResNet model and training it on a different dataset.
Was this the inspiration for your own 3D model also?
Yes, in fact, it was. We followed similar principles that is used in our ResNet 18 3D model and transferred the weights of those intermediate layers back from the Med3D model.
Furthermore, there was transfer learning by freezing all the layers, except the fully connected or FC layer, to identify the bleed labels accurately.
This is really fascinating. But what is the result when you attempt to use this model?
Our initial plan was to use the model to predict all 14 labels, but this wasn't very successful. So we scaled down the model and tried a second iteration where we just focused on the 6 label classes.
However, even with a reduction in the number of labels, it did not yield better results. Therefore, we opted to use a multi-step model, which is to first predict the presence of a bleed, whether ICH positive or negative, and subsequently the type of bleed and which side of the bleed is present in the brain CT scan.
From a healthcare perspective, the multi-step model would definitely seem intuitive to help and aid hospital in diagnosis.
So while that is true, unfortunately, all 3 models seem to continuously predict the same labels for all the prediction as shown in the confusion matrix for the 3 models.
What's actually the reasons for these similar results?
One of the reasons that we identified could be because of insufficient amount of data that is being used for training. We observed that the train loss did not even go above 0 after continuous training beyond 10 epochs.
However, the exploration for a proof of concept using the 2D model was definitely more promising.
How is it architecturally different from 2D CNN model?
Well, the 2D CNN model requires slice level labels where each axial slice of the CT scan needs to be labeled. But the dataset that we had only had examination level labels. This means that all the axial slices within the CT scan are labeled as the same as the CT scan itself.
To illustrate this, refer to the image in the slide. For the examination level labels, there was 1 positive slice, hence the whole bag was labeled positive, even though there were 2 other slices without any positive labels. So if we were to input the scan slice by slice using their examination level labels into the classifier, we foresee that the model training will converge poorly due to misclassification of normal slices as belonging to the positive class.
Oh, this actually sounds like a potential issue with the model. How did you guys manage to address this?
To handle datasets with examination level labels, we decided to use a method called multiple instance learning. So this treats each dataset as a bag that contains multiple instances. So each bag would be labeled positive if even just 1 positive instance is present in it. So we can see this from the illustration above.
Ah, I see. That is why you chose to use weakly supervised learning method together with multiple instance learning to improve your model training.
Indeed, the weakly supervised learning method involves training a model with only examination level labels. So this method helps to improve the learning outcomes when complete slice level labeling is not available. As such, complete labeling is difficult and expensive to perform.
An additional point to note for the MIL model, before feeding through the final classifier layer, the instances within the bag are added together into a combined feature vector.
However, instead of treating all slices equally in the combined layer, we integrate an attention layer prior to this aggregation process. So this adjustment allows the model to assign different weights to each instance, thus prioritizing those layers that are more likely indicative of the bag's label.
In the context of our project, the attention-based MIL framework allows the model to focus on specific slices within a scan that indicates the presence of hemorrhage, despite only having examination level labels. So this method effectively prioritizes informative features while diminishing the influence of less relevant ones, enhancing the model's ability to generalize from limited supervision.
Thanks for the explanation. I'm curious, how does this performance of this 2D method vary from the 3D results?
Okay, so the 2D model definitely performed much better, especially when we focus it on the 6 label datasets to identify specific brain bleeds.
Shown in the confusion matrix, the model seems to be quite conservative, incurring more false negatives than false positives. But this generally provides a high recall, which is still useful given that the current CT scan screening process still involves a human eye to verify the results.
The model managed to achieve a consistent F1 score of around 0.71 in both the validation and test sets, which was quite promising.
Yes, definitely. how did you guys actually the model training improve over time?
Okay, so we observed that that with more training, there was a progressive decrease in the training loss, which showed effective learning on the model itself.
Furthermore, the F1 score improved over time, showing strong generalization ability of the model itself.
Wow. Okay, this is really great in helping us how well the 2D model works. But let's compare the 2D and the 3D model when we talk about long-term deployment. How was that?
When we look at the performance individually, the 2D CNN definitely performs better. As you can see, it achieves a higher F1 score of 0.71.
So 2D models generally require a lot lesser computational resources and is far more adaptable when having an incomplete data set, as we have highlighted earlier.
What about the 3D model though? Why did the 2D model outperform the more complex 3D model?
Well, the attention mechanism employed in the 2D CNN facilitates the identification and prioritization of informative features within each CT scan. So this mechanism allows the model to focus on slices that are more indicative of pathology. Also, the 3D model inherently has training challenges because it was trained on non-specific datasets. There was also a limit to its learning as we only unfroze the final layer for training due to computational constraints.
Thanks for the explanation. An important point to note is that the current healthcare landscape doesn't accept black box model, which would mean the 2D model you have created will need to integrate well with the existing model used in the hospital today.
Yes, that is very true, Kin Hong. Today, GradCam, a commonly used XAI method for convolutional neural networks, is already being used in healthcare industry. And it would be very beneficial for healthcare professionals if the model you have designed can incorporate GradCam to actually highlight the CT scans to show even better results.
That is very true. As you can see above, we have already integrated GradCam into our solution. With this heat map, which illustrates the areas most influential in the model's decision, this can increase trust and reliance in AI by doctors.
While we do hope to eventually benefit as many people as possible, we do also want to improve the model performance gradually to augment computer-aided diagnosis.
Overall, this product you guys have shared with us is definitely a game changer, and the potential to improve computer-aided diagnosis is definitely worth investing in.
Very much, Achilles. As demonstrated, not only is our model able to effectively identify hemorrhage presence in brain CT scans, but in day-to-day life, it can also help to value add by providing improved accuracy and efficiency for radiologists.
I guess one key challenges you might be facing is the current model requires significant computational resources, and so with the current resources you have, the training will take a long time.
Well, that's true. And we do hope that when we scale our product and work on improving the model, these kind of computational resources can be also overcome.
At the end of the day, we want to ensure that the model augments radiologists well, reduces errors, and improves patient care overall.
Wow, that is a fantastic and very noble goal, guys. And it was actually a very enlightening sharing by all our panelists whom we have had today. Thank you very much to all our speakers here today. And more importantly, thanks to the audience. And we hope that you have enjoyed yet another episode of MedTalk, where we talk about all things medical and tech. See you next time.